Okay, welcome to an Orbiter 2016 video. This is going to be a short video series about how to execute low thrust orbital escape maneuvers and to combine them effectively with TransX. And to do this, I'm going to start out by pointing out where it is that the standard use of TransX to execute burns begins to fall down when the engine thrusts begins to become really quite small, and to show that, well, to demonstrate a tool written in Python that is available for download and for use by everybody, that allows you to overcome the limitations of the stock TransX tool to execute some low thrust burns. And in principle, it's possible eventually to get down to thrusts which are of the range of milli-G levels. So that's roughly, I don't know, 1,000 times weaker than the stock engine capability of the Delta glider in Orbiter. So to get the ball rolling, this particular part is just going to concentrate on the standard use of TransX. So just to run through quickly how the tool is used to perform standard maneuvers, to show that if you weaken the thrust of the engines, the accuracy of TransX begins to fall off markedly for some of these escape burns. And that'll be it for this part. And the next part on this short video series will basically then introduce the Python-based tool, which can be used to perform much more accurately these low thrust escape burns. We'll just go through the standard Delta gliders engines and run through how one would use the tool for that case, and then we'll step down the thrust of the engines tenfold, then 100-fold, then 1,000-fold, and just see what kind of we'll see how this tool operates at those particular levels. So okay, just to begin with then, we are going to demonstrate how TransX is typically used to execute an escape burn. Now, this is my way of doing it. Other people have got variations on the theme. I'm not going to quibble about what is the right or the best way of doing things, but this is the way that I do it, and I think it's fairly consistent with the way that other people will do it too. The starting point for this is a stock Delta glider scenario. I think it's landed at Cape Canaveral. It's the Delta glider sitting on a launch pad at the Cape, and I'm not going to go through the full sequence of launching the Delta glider into orbit from this particular launch pad. I want to focus on the execution of the burn, so basically I'm going to use a scenario editor to put the Delta glider into orbit. But I have to first know what orbit I want to put it into, and so I actually have a TransX escape plan listed over here in this box, which is actually it's an optimal Hohmann transfer from the Earth to Venus with a departure date of MJD 57728.1337. Now, it doesn't really matter where this plan came from. It actually came from using the European Space Agency's freely available PyCap program. But it exists. This is an optimal Hohmann transfer, and we're going to just take it as it is, put it into TransX, and then put the Delta glider into the orbit that's consistent with that burn, execute the burn, and demonstrate a few things. So let's go with this. The first thing to notice is that the MJD is 57728.1337. The MJD currently in orbiter is 51981.6, so we've got a difference of around about 6,000 days, about, I don't know what's that, nearly 20 years, 15 years, something of that sort. Is that right? No, 6,000, anyway, it's a long time separation. So what I'm going to do is, first of all, I'm going to use the scenario editor. Just move that out of the way. Use the scenario editor to change the date to something that's a bit closer to the maneuver date that's been generated by ESA's PyCap program. The MJD I'm going to use is 57728.0, so it gives us about a sixth of a day to set things up in readiness to escape from Earth. So I'll put the MJD 57728.0 into the scenario editor, and then I'll go apply. I will go apply if I can get this thing to work. Apply, there we are. Now we've moved forward in time, what's 6,000 days or give or take, to a date which is the 6th of December 2016. Okay, so we'll close that out. So now we are close to the maneuver date. The next step really is to start playing around with TransX in the time-honored way. Now, this isn't the tutorial on how to use TransX, so I'm going to assume considerable familiarity with the way the TransX works. And if you're not comfortable with that, then I can suggest that you go and have a look at some of David Courtney's YouTube video tutorials, demonstrations, whatever you want to call them, that are available on YouTube, and go through that. And basically there's an awful lot of explanation available via that means to let you know how to use TransX. But assuming you know how to use TransX, then basically we're going to load up TransX on both sides in our glass cockpit view, and we're going to go and select the escape option in setup, and then go forward on the right hand side, and we're going to select Venus as the target planet. And we're used to selecting Venus here because we know that this transfer that we've established earlier is actually an optimal Hohmann transfer from the Earth to Venus on a particular date in question. So having done that, we're now going to go and view over to the eject plan, and we're going to start putting in the escape plan that came out of PyCap. The first thing to put in is the prograde velocity, and we're just going to copy the number straight out of the plan. That's minus 2583.170. Okay, that's the first one, and now we'll variable over to the date, and we'll put in the correct date, which is 57728.1337. We'll go with that, and then we'll variable over to the outward velocity and put that one in, and that's 1566.460 meters per second. And the last one is the plane change, and we'll put that number in, which is minus 1364.955 meters per second. And voila. We now have a closest approach shown in TransX on the right hand side of 2,814 kilometers from the center of the planet. And if we go forward, we can see that the maneuver, the arrival trajectory at Venus is tunneling through the center of the planet. So indeed, this is a trajectory plan that will take us to Venus on the date in question. So let's go back. Okay, Now, we are currently 0.133 days away from our target departure date, and we're currently sitting on the ground, and rather than go through the whole launch sequence, what we're going to do is we're going to use the scenario editor once again to go and put us into an orbit that's consistent with this escape plan. So very quickly we're going to go and hit the view on the left hand side, and as soon as you do that you get all of this information down here popping up. And the two numbers that I'm most interested in at the moment are the inclination and the longitude in the descending node, the LAN, in the first two rows of this new block of numbers. These specify the orientation of the departure orbit, and I need to, however I get there, whether I use the scenario editor or whether or not I launch into this orbit, I need to end up in an orbit that has the same inclination and the same longitude of the descending node as the escape plan trajectory would have us. So I'm just going to use the scenario editor quickly and just get that out of the way again. Hit edit and then go to the orbital elements, and now I've got a bunch of stuff up here which I can change. Now I'm going to put myself in a 300 by 300 kilometer circular orbit. Nothing particularly magical about 300 here. I could have chosen 250 or 350 or some other number. I could have even chosen a non-circular orbit, but I'm going to go with a 300 by 300 circular orbit, and simply because the numbers are convenient. To do that, I have to choose a semi-major axis of 6671 kilometers, and then I want to put it in meters, so I'm going to add 3 more zeros, 6671,000 meters. The eccentricity I have to change to 0 because I want a circular orbit, and now I want to change the inclination to the number that TransX is showing, which is 24.31 degrees. And finally I want to change the longitude of the ascending node, the LAN, to 285.9 degrees. And that's it. Those 4 numbers go in, and hey presto, I am now in a circular orbit, 300 by 300 kilometer circular orbit around the Earth. And because I didn't take off properly, my landing gear is down, so I'm going to hit G to put up the landing gear. Close out the scenario editor. Now on TransX on the left hand side we have a slightly awkward presentation of our orbit, so I'm just going to change that by going over to View until I get the Setup option, and then Variable over to Graph Projection, and then change it to something that I like, which is going to be Plan for sake of argument. Okay. Now I'm going to view back over to the escape plan, and I'm going to change the PE distance to the 300 by 300 kilometer radius, which is 6671, and then 3 zeros for meters. So there you are. Now what do we see here? Basically on the left hand side we've got a picture of the Earth, and we're looking down on top of our orbit. We're currently where this green line is, sitting over here, and the green circle is our current circular orbit around the Earth. The yellow dotted line is the hyperbolic orbit that we need to have after we complete our escape burn, so that we can achieve heliocentric orbit, shown on the right hand side, that gets us from where we are now, which is up here at the end of this blue line, all the way down to the rendezvous with Venus down here. So the way this has worked is that basically we've put in the heliocentric picture of the world to get us with a rendezvous with Venus, and this has been translated on the right hand side in TransX into an escape trajectory that we need to have when we are just leaving the Earth's orbit. Now, if we had an instantaneous burn, if we could do everything absolutely in 0 time, then we would do it when we get the screen line wraps around here to and overlaps the yellow dotted line that's coming out from the center. And that would be fine. We would then have exactly match the hypothetical yellow orbit, and we would be exactly on our plan from Earth down to Venus. And that's all good. In practice, we can't execute the burn instantaneously. The power of the Delta Glider engines is finite, and so it's going to take a finite amount of time to execute the burn. So we're going to have to set up the burn in a moment. But the first thing we want to look at is the relative inclination. The relative inclination is 0.009 degrees out of whack with the true plane. So our orbital plane is 0.009 degrees out of plane with the plane of our departure trajectory, which is this yellow line. So we're almost in plane, but we're not quite. Now I could spend some time fiddling around with the relative inclination. For example, I can change over to linear RCS, and then if I go into the prograde orientation quickly, and I'll just hit the time warp button, change over to an orbit HUD, and change the scale to 50-degree field of view. Right, now what I can do is let's turn off the prograde there, and I can just come hit 2 and 8 to try and reduce the relative inclination. So I'll just do that wrong way, so I'll go and hit 8, and that will bring it down somewhat. So a few taps of linear RCS, probably half a meter a second or so, has reduced the discrepancy down to 1/1000th of a degree, or 2,000th of a degree. I can live with that. I'm not going to play around with this anymore. It's not really the focus of what I'm doing here. If you really want to be finicky, though, you'd try and get that as close as possible to 0. Now, the other numbers on this left-hand side in the TransX say that the amount of delta V that we require to escape is going to be 3,693 meters per second, and the time to perolapse is going to be around about 3,000 seconds. But given that we've got a finite amount of thrust that can come from the Delta Glider engines, we need to begin the burn in 2,900 seconds. Okay, the easiest way of getting to executing this burn is actually to load up burn time MFD, and again I'm going to assume you know about burn time MFD and how to use it, and simply hit the get button, and now we've loaded in the TransX plan, which is to execute a burn of 3,903 meters per second in 2,950 seconds, which matches what we have here. The final thing we need to do is to orient our vessel so that we are pointing in the right direction to execute the burn. To do that, we're going to go and view turn the maneuver mode on. Variable. Turn auto center on. Sorry, just let me play around with this for a second. It's been a little while since I've done this. The maneuver mode, turn that off. Variable over to prograde velocity, I want to put in 3693. So I want to put in 3693. And now I want to change the time, the burn, variable over to the date, then adjust the setting down to hyper, swing it forwards, until the two overlap each other. I'm not going to go through this in any detail as to what I'm doing here. I'm just going to do it. And they are overlapping just about there. Okay, so our maneuver now matches our plan, and now we get the target view. And now I want to go back to here and I want to turn the auto center on. Now this is an efficient way of maneuvering the delta glider into the right orientation, but doesn't really matter. I'm just going to go with it for the time being. It's going to flap around in the breeze a fair bit. It's going to burn a lot of fuel, RCS, in executing this maneuver, but I don't care for the purposes of this demonstration. So it's going to settle down, and the time to maneuver is 2,700 seconds, give or take. So we're going to do a little bit of time warp to get closer, and even at 10x it's going to be quite a long way to go, so we're going to go up to 100x. And we need to do a bit more. 250, 260, 270. Just as we go through the 270 mark, it's going to flip. And now we'll increase the time warp up again to 100. Oops, it's becoming unstable. And we're now down to 900 seconds away from the start of the burn. So this is just a standard TransX protocol for executing these escape maneuvers. After we've done this and we've gone through the exercise of reducing the thrust by a factor of 10 and gone through the same exercise in TransX and pointed out that there is a little bit of a problem, we're going to come back and do this again using a more sophisticated tool and actually do it in a way that I prefer to do it, and it's actually more accurate, even down to really very low thrust levels. Anyway, we're 600 seconds away from the burn. Let's just put in a bit of 100x. Time to ignition down to 50 seconds, 20 seconds, 7 seconds, and now we're just going to let this thing burn. The burn is going to take 156 seconds. There we are, we're burning. I'm just going to get through this quickly. Nearly there, down to about 20 seconds, come back to real time. I'm going to turn the auto center off shortly. I'm going to get down to 10 seconds left. There we go. That's off. And we're pretty much done. It's going to cut off now. Okay, that's really all we need from that. So go back to the TransX view. So that's our burn completed. And we are a little bit light. It stopped early. We really needed another 1.844 meters per second. So let me just go back to the let's go back to here, turn the maneuver mode off, view over to here. Delta V to match the planned one is 2.276 meters per second. So let's just tidy this burn up by putting in a bit of linear RCS. So the delta V, oops, just overshot a little bit there. It's good enough. So we've done a little bit of tidying up with the linear RCS to make sure that the delta V amount is close to 0. The inclination is still low. It's still the same 0.002 degrees that it was well before we started the burn. And the semi-major difference, what is the semi-major difference? This is the angular difference between the what's known as the argument periapsis of our hyperbolic target orbit and our actual orbit. So we're 0.07 degrees off in alignment there. And what we can do is just go to prograde, tidy that up, let it settle down. Okay, now use some linear RCS, some 1 and 3 to just get that down to 0. Now we have to use a fair bit here. It's a standard technique, so we're probably going to be burning in total 5 or 6 meters per second just to tidy up this burn. Getting close, and there you are, pretty much it. Now we could do this a bit in a slightly more refined way. We can get the delta V down to pretty much 0. We can get adjusting so that our inclination is essentially 0, and our semi-major difference is essentially 0 if we play around it just long enough. And we'll burn roughly between 5 and 10 meters per second doing this tidy up configuration. But what it does is it has us exactly matched with our target hyperbolic escape orbit. Great stuff. And this procedure is fine. I mean, basically, it's perfectly functional, and the cost of tidying things up at the end of 5 to 10 meters per second, not a big deal in the scheme of things. Certainly within the tolerance with which we use our orbiter, which is probably within plus or minus 10 meters per second for most of the maneuvers, at best. So that's all fine. Why do anything different? Well, the problem really comes when we start using more realistic engine thrusts. If we load up burn time MFD again, we have an engine ISP of 40,000 kilometers. Well, it depends what units you want to use, but it's 40,000. And that's roughly 10 times higher than real engines have. And that makes a huge difference. So if we reduce the thrust, because we have this very high engine ISP, we have a huge engine thrust of 320,000 kilonewtons. These are very, very powerful engines, far beyond the capabilities of anything that is realistically out there today, or likely to be out there for the foreseeable future. So what we can do now is run through this again with a lower engine thrust and see what impact that has on how we use TransX. And what it's going to show is that things begin to look a little bit less robust, and that the areas that TransX introduces begin to grow rather significantly. And if you then consider even weaker engines, those that then might come from, say, an ion thrust or some other low thrust device, which is even weaker than the sort of standard 4000 ISP engines, then you're looking at errors from TransX that are just simply unacceptable, and you have to have a better way of executing these escape burns. And that's the whole point of this exercise. Okay, this has gone on long enough, and probably longer than I really expected it to, so I'm going to stop this particular part here. And in the next part I'm going to go through and do this with TransX exercise again, but set up the Delta glider with a lower thrust, and then I'm going to show how you can do this in a better way. Okay, so that's it for now. Stay tuned for the next part, I guess.